display ads, search engine marketing, email, or mobile ads, and offline channels, including those traditional channels like TV, print ads, or radio. So as investors, they have the common desire, a natural desire to understand what channels are more effective and what channels are not so effective in terms to optimize their KPI, key performance indicator. Particularly for a single conversion, they want to assign the credit of this conversion to the multiple media touches a user received before the conversion. So in this talk, my colleague Anny and I are going to share some experience of leveraging Apache Spark to build algorithmic attribution models. First, I will give a quick overview of attribution, and then Anny will talk about our algorithmic attribution algorithms and also its Spark implementation. Finally, Anny will share the lessons we learned through this process. Before we talk about attribution, let's first understand the media path of a user in the online journey. So when I was preparing these slides, I was thinking about skipping it because, not because it's not important, it's actually very important, but it's so familiar to us because we have all been there. We have all been such a customer like this guy. But let's still take this guy as an example. So he saw a display ads either on a desktop or on mobile app and get interested, get some impression is about Adobe Creative Cloud. By the way, it's a great product. So he decided to do more research on it because of this ads impression. So he searched keyword Creative Cloud on Google and then click a sponsored link. That's a paid search touch. But he didn't do anything because he needed to think about it, to compare other alternative products. But a few days later, he go back, do a search again, and this time he click a organic link, which is an organic touch. And then he decided to register as a free user because it's free, why don't give it a try? And after he becomes a free user, he receives some emails, talk about great things about Adobe Creative Cloud, and a few days later, he converted. He become a paid user. And so we call this a positive path or conversion path. Alternatively, in some other scenario, people may receive all kinds of touch points and didn't convert. So that's a negative path or non-converted path. So basically, that's the process. So then what is attribution? So we'll talk about attribution or digital attribution. The only difference is attribution, we consider both online channel and offline channel. But by digital attribution, we only consider online channels. In this, for the scope of this presentation, we only cover the digital attribution. So basically, an attribution model determines how credit for conversions are assigned to the multiple touch points, as the example we just saw. So why we do this? Actually, it's a very natural way to do decision making. Actually, we are doing attribution every day in our daily life. For example, most big companies do performance review. Why we do performance review? Because we want to understand what you did in last quarter or in last year, which is good, is effective for your performance, or which are not so effective for your performance. On one perspective, you want to really monitor your performance, what you did. But more importantly, you want to plan for the future. You want to do what you did good before and try to avoid doing what you did bad before in order to optimize your performance. So back to the marketing scenario, it's exactly the same thing. The marketers, the business owners want to understand the performance of the marketing spending in the past. But more importantly, they want to plan for the future, to optimize the KPI in the future. So that's why we do attribution. And here is an example of attribution, right? So you have one conversion, and then you assign some credit, like 30% to the email, and 20% to a touch before the email, and so on and so forth. But now the problem is how we assign the credit. to make it sensible to really quantify the effectiveness of different media touches. So here we summarize all the popular digital attribution models in terms of 3 attributes. The first attribute is, do we consider all the touch points along the customer journey? The second one is, do we consider the time decay? Because naturally we will think display impression you received 30 days ago is not as effective as the impression you received today, because we have the memory tend to forget the old things, right? And the third one is whether it's data-driven versus rule-based, whether we learn the information, the effectiveness from the data, or we just judge by our expert evidence, right? So, so the first type of model is last interaction or first interaction or last or first particular channel interaction. So we can quickly guess the strategy from the name, right? Last interaction, that means you attribute all the credit to the last touch. Like if you have a pay search and go to the website and purchase, you attribute all the credit to this pay search touch, or the first interaction. So consider all the media touch points? Obviously, no. It only consider last or the first. Decay, no. It's only consider one touch point. There's no decay effect at all. It's learned from, it's not learned from the data. It's a rule determined by human judgment. The next one is linear. It's very simple also, right? So instead of only attribute to one touch point, you assign the credit linearly to all the touch points, uniformly to all the touch points in the conversion path. And it considers all the touch points, obviously, but there's no time decay. It's also a rule-based. There's no data involved in the decision. And the next one is time decay. So, which is similar to linear, but you add a time decay. You put more weights on the near the touch point near the conversion, close to the conversion, and less weights to the old touch points. So it's considered time decay, but it's still a rule-based, unless you learn the decay parameter from the data. So that's a modified version of decay method, which is slightly data-driven. And position-based is, which is similar to the linear, but you assign maybe more credit to the last touch, more credit to the first touch, and then split uniformly across the touch within between. So it's considered all touch point, but probably no decay in the uniform assignment. So the last one is algorithmic. It's considered all media touch points, and we also can add a decay parameter to address the decay effect of the touch points. And we build models to learn the effectiveness from the data. So it's data-driven. So why this is, we think this algorithmic method is better than the other rule-based method. Here's some simple words for the comparison. The rule method is you determine the weights based on rules, based on human judgment. But algorithmic method is more data-driven. You learn it from the machine learning or statistical model to determine the weights. I think the fundamental difference is we can use an example. So many advertisers or marketers actually do this type of experimentation. They send out placebo ads like saving water for California, which is a very good ad, but it's just not relevant to your business. And you can imagine that if you do this campaign and using first touch, last touch to do the attribution, those ads will get credit for sure, because some users just randomly see this ad and then convert. Although we know that those ads provide zero lift, zero incremental probability to the conversion, they still get credit based on the rule method. The fundamental reason is the rule method doesn't address or measure the incremental conversion probability or the uplift of the media channel. Instead, it's just if it presents, it gets credit, which doesn't make too much sense if you think it's using common sense, right? So yeah, with all this, I would like to hand it over to Anny for the rest of this presentation.
Hi. I actually at first thought I didn't want to write so many things in just one slide. But I just want you to get some basic ideas before I jump into the algorithm and modeling stuff. So the attribution model we built is a combination of distributed lag econometric model and discrete time survival model. It is a distributed lag econometric model, meaning the time effect is taken care of during the process. So as William mentioned before, if an event happens very far away from now, it will have less effect on the final conversion. If an event happens just now or very recently, then it will have much power on the final conversion. So they are different, and we want to take care of that. And it is a discrete time survival model because the user doesn't enter the experiment at the same time. We usually use a continuous time survival model because the users have a universal start and a universal end, but in our case, they don't. Some users got their first touch point long ago, at the very first beginning of the observation window. Some users got their first touch point very recently. And also, they don't have a universal ending. So like the measure of the effect is not a one-time thing. The measure of effect is, the effect is measured by day. So they also don't have a universal ending. That's why we model the events as a discrete time survival process instead of a continuous one. And also, there are some highlights we like to mention here. So the basic idea of our model is to compare the media touch points in positive paths versus those in negative paths, and thus derive their effects from the touch points. And also, we use the logistic as a link function to connect the predictors and the y variables. We also use time decay parameters to take care of the time decaying effect of the media touch points. This is something we always like refer to and have focus on, because the more distant the event, the less power it will have on the final conversion. Also, this part is something that many current models don't take care of. And we fit media touch effects and the decay parameters simultaneously. We take care of the time decay parameters. That means we actually have two types of parameters. One is the media touch effects, and the other is the decay parameters. So in the model, we have to fit model and solving these two series types of parameters. I will tell you more about how we actually do this. And also, we have constraints on the coefficients. For the time decay parameters, we require it to be between 0 and 1. We know that it doesn't make sense if a decay is like above 1 or it's below, it's smaller than 0. So actually, from this point, according to this standpoint, solving the model is actually a constraint optimization problem because we have the boundary constraints. The decay parameters is between 0 and 1. We also use stratified sampling because among the whole population, the conversion rate is so low. There's only a tiny small population that actually convert. Of course, we hope the population will grow, but the current case is they are still small compared with others. Also, there are some bias inherent in the data. First is the duration of exposure. As I mentioned before, some users enter the experiment quite early, while others enter the experiment very recently. So actually, the duration of exposure is very different. Some people have been receiving touch points for 1 month or 2 months. Some have been receiving touch points for only 2 days. So we can't treat them as like the same kind of paths because the exposure is totally different. So, and also like the users, they are human beings. They have their preference even before they got their first touch points. Some people heard about Adobe quite long ago. So even if we don't give them any touch points, they will be very likely very happy to subscribe to our products. But others people know maybe know nothing about Adobe. And if we don't give them any touch points, very likely they will never convert to our products. So their preference before they got their first touch points is different. So they are different population. So to deal with those kind of bias, we use some methods like variable controlling and also some causal modeling strategies. So we build the model based on those assumptions and highlights I mentioned before, and we established the likelihood function based on the model. So we solve the model by maximizing the likelihood function, as we always do in the optimization problem. So there are actually a very special strategy I would like to mention. That is tokenization. So the effect is of a media touch point is hardly doubled or tripled, even if it is sent repeatedly to a customer twice or 3 times in a very short period. Such as you just go through, you just like walk on a street and you see the same advertisement from Adobe 5 times. Will you be wow for 5 times, or you just have the impression, oh, I saw that ad? Very likely, you just have the impression, oh, I saw that ad. So this is why we have to use tokenization. Tokenization is used to group neighboring events together. So even if you see the same advertisement 5 times, you will see in your heart, you just have the impression that I saw them once. Such as you got 5 display events continuously in a row. And so the tokenization will treat them as just 1 token, or maybe 2 tokens according to a certain compression rate. So we talk so many stuff about like the modeling and also about our assumption and the bias. So why do we choose Spark? This is actually like our decision process. So we have the raw data. We have the database to have the raw data, and then depending on the size of the data, we can choose some normal tools like Python, R, Java. They are very popular. Then they have many resources, many libraries. You can easily find an algorithm you like in their libraries. But because the data is very huge, so we have to use some big data tools like Hadoop, like Spark, and also many other things. And also for the big data tools, we can implement a rule-based model, or we can try to implement an algorithmic model. Because we want to do an algorithm, a model, a machine learning model, so we kind of find it hard to implement it using Hive or Pig or Impala or Presso. They are perfect when you are doing some kind of a BI model, or when you are just trying to get some insights from data. But if your model needs very intensive computation or many iterations, then maybe Spark is the right choice. So that's why finally we go along this decision tree and we choose Spark. So this is the data processing and the stitching process. So it's not that like that the data comes in and then I throw the data into the model. The data comes in an event level, and then we aggregate them into a path level, and then finally we build the model on the paths. So let's talk about the event. The data comes in an event level. Every line is an event. There are multiple types of events. There are media touch events, conversion events, and other user behavior events. Also, in each event, there are many data fields, such as customer ID, timestamp, event type, campaign ID, and etc. So to build the path, we have to stitch the events of the same customer by ID, and then generate paths based on the result of the user. So if the user converts finally within the time window, then we say this is a positive path. Otherwise, if the user hasn't subscribed to our product yet in the observation window, then we call it a negative path. As I mentioned before, the number of the negative paths is much larger than the number of the positive paths. And then we have the positive path and the negative path. We build a model on those paths. And so each path is a record, like the row, like every row in the data. And the positive and negative label is the outcome, like the y variable in the model. So we didn't get the perfect model at the very first beginning. So like this is how we build the model, improve our model step by step. So the first model we built is a fixed time decay model. So the time decay is fixed in the model. That relieves our burden because then we have only one parameter. That's the meter-touch effects. So we use the logistic regression using the MLab logistic solver. So I think it's quite good. Just now in the first talk in this session, the gentleman talked about the logistical regression in the MLab. So I used that solver directly to solve the first model quite smoothly. And the second model we built, and then we said, oh, we want to make some like contribution to the attribution model. So we use the time decay as a parameter instead of prefixed. So now we have two types of parameters, the touch point coefficient and also the decay parameters. So now I couldn't use the MLab logistic regression solver directly. So I optimized alternatively in each iteration between the two types of parameters. I'll talk about that further in later slides. So the solver I built is actually a customized version or an extension to the original MLab logistical regression. So I think actually we can like extend some of the algorithm provided by the MLab to meet our customized needs. And I think the model I built is an example for that. And then we, after the second model, we found some problems like I talked about the bias. So we have to use some introduce some causal modeling strategy to deal with the bias inherent in the data. So the strategy we used includes some, at first we use match sampling, but then we may consider some propensity score sampling, so before the data enter the model. So that is the process of our algorithm evolution. So our data is actually stored, so the Spark cluster, I'll talk about that first. The Spark cluster we maintained is actually built on the AWS Amazon Web Service Cloud, EC2 Cloud. The data is stored in S3. There is a benefit of like building the data on AWS and storing the data in S3 so that the Spark cluster could directly get data from S3 and write back to S3. It saves us both speed and also cost, actually. And for the monitor, we use the web UI provided by Spark standalone cluster. So actually, as time goes on, in order to like meet some customer needs and also to incur some to make the environment more secure, we actually add two additional layers of a security measure. So between the S3 and our Spark cluster, we use server-side encryption. So like the data has to be encrypted before writing to S3. So now you have, there's some other, there's more trick you need to do before you write your data back to S3. So the Spark save as text or some function couldn't write directly to S3 now. And between the Spark cluster and the web UI, we also add additional layer for security reason. We add the Bastion host. So now you couldn't like log into the Spark cluster directly. You have to go through the Bastion host, and through the Bastion host, you can go to the Spark cluster. So for the web UI, we couldn't see the web UI directly now, and we have to use some SSH forwarding, that kind of skill, that have techniques to get the web UI. But although it may cause us some inconvenience, but it greatly increased the security of the environment. So this is actually, I provide you some detailed implementation workflow. So there are two basic major modules of my algorithm. The first one is a model building, and the second one is the attribution. So in the model building, there are four major steps: data processing and stitching and tokenization, I talked just now. And it also generates the paths from event to path. And so it also generates paths. And then we build model on it. So, and we run the parallel algorithm on the model. And then finally, we'll save the model parameter to S3. On the right side, the attribution side, there are also 4 major steps. The first one is also data processing and tokenization and stitching. And the second one is to retrieve some model parameters from S3. And the third one is generate only positive paths. You don't want to assign the credit of non-conversion to the touch point, so we only need the positive paths in the attribution part. And the fourth one is the attribution with the model. Is to report the attribution and save the attribution results to S3. All the 2 modules are running on Spark on EC2 cluster. And also they have like very active interaction with S3. So for the model building, it gets data, raw data from S3, and also it output model parameter to S3. For the attribution part, it also gets raw data from S3. And it output attribution result to S3 as well. So the customers could directly get data from S3 or from other database. So those are actually about the, our whole like modeling and algorithm stuff. So during the whole process, I learned a lot from like the whole model building process. The first one I would like to share with you is the memory management. So at first I got the data and the data is stream based. When I run the data, the job always fails, although the data size is not as large as the whole total memory. So I was a bit confused. Then I realized there was a group by in my code, and the group by actually needs a lot of shuffle space. So that's why the job always failed. So now before like the data enter the model, I hash the data from stream-based to byte-based. Then use the byte-based data to enter the model. Now the size is actually decreased tremendously, and the job no longer fails. I intentionally put a slide here about the web UI, such as the original data is about 200 GB. And then after this hashing, the data finally enter the Spark cluster will be only 50 GB or even less, even like 30 GB or something. And also the second lesson I learned is about write separate classes for model training and attribution computation. So you see the 2 modules, they both need raw data from S3, but actually they need different information from S3. For the model building part, we need like what type of event this was and like what's the final result of this path. And so it's actually it's just like several data fields among all the fields provided by the events. So we actually need only a small portion of the information each event carry. And for the attribution part, attribution model, because finally we'll need it to output the results to S3, and customers could directly read the results. So actually we need much more information from each event for the attribution model. So that's why I write separate classes for different modules. So in that way, the module building part, it needs intensive computation, needs many iterations. You don't need to carry so much information around. You only need to carry just that several data fields of the event. So this is the 2 lessons I learned about the whole building part. And also, when you are running some Spark job, you always meet with some very annoying out-of-space error, such as Java heap out of space, or like the worker, there's no other space in the worker that you have to drop some cached part before you actually before you actually cache other items. So those those errors are normally met, and if you met some Java heap out of space, you may want to increase the Java heap before when you are running the algorithm. And if you see there's no more space on the worker, some errors like that, you may want to check some specific folders on the workers. Actually, I put some slides here, but maybe because some updating issues, it didn't show up here. You can check up some like the MNT folder in the workers, or some the Spark work folder in the worker. We can communicate that if you have some questions. You can check that to see if that folder is actually filled because of some previous failed job. According to my experience, sometimes the job, the previous failed jobs will not empty itself automatically. It will remain in that folder, and then the later jobs couldn't run. And also, there's some, if you see some like the cache size is too large, like in the log, you see there's no more space for cache. You may want to you may want to increase or decrease the memory fraction of each worker so that you can control how much memory you want to assign for cache, how many memory you want to assign for other actions. Yeah, oh, actually, yeah, I put it here, so you can check the Spark work folders, and also you can check the MNT Spark folder in the workers. And also, like, when I'm writing the data, when I'm writing the code, I constantly need some libraries from Java and some objects from Java. In Scala, many objects are serialized, so you don't need to worry about it when you are doing some map job or transformation job. But you may want to worry about it when you are using some Java objects. So you may want to use some KRL registrator and then register it before you actually put those objects into the map task. And nothing like this is some experiences I got by myself. So like sometimes you see an error from one line, but that error actually doesn't come from that exact line. This is because Spark is using some lazy evaluation. So it will only report errors when it is doing the action task. The action task includes something like print line and something like count, something like take several lines. So sometimes I'm confused because I didn't make any mistake in those action lines. So those mistakes actually may come from the transformation line quite ahead. So like you wanted to first do some transformation on each event, and then you wanted to print line. So the error actually occurs in the transformation, but it won't report until the action stage. So in that case, we may want to check some code further ahead to make sure that the transformation step doesn't make anything mistake. So like the map, the flat map, those kind of comments belong to the transformation. And also the adjustment of step size. So I also use the stochastic gradient descent in each step. So that also need me like to adjust the step size for each of the step. Famously, the first two models I used, I didn't use some causal modeling strategy. So the data entering the model is quite huge. So then I use some step size that is a little bit bigger. And then the third model, I use some causal modeling strategy. And the data was actually greatly decreased before they enter the model. So I still use the same step size because I suppose the model doesn't change that much. But then the trouble caused because the step size is too large. And so you have to, so when you are doing something like I did before, such as using the gradient descent, and you want to adjust the step size, pay attention to how much data actually enters each iteration. And also tokenization, because like I said, when you come through 5 displays, sometimes you want to treat them as 1, but in some occasions, you might want to treat them as 2 or 3. So you might want to include the weight in the tokenization strategy. Instead of like, if you meet 10 displays, you still treat them as 1. You may want to treat them as 2. So actually, that's all the stuff I want to share with you today. Thank you. Yeah, do you have any questions?
So you don't want to ask a couple questions one at a time. So the observation window you mentioned is that, how did you set that? Is that relevant to the campaign period?
The observation.
Can you repeat the question?
Okay, so you mean like the
Observation window. So a certain time you decide this user did not convert, right? And you stop measuring. How did you decide that?
The time window now is decided like based on some experience. So like, yeah, we take maybe 3 months or something as the observation window, but it also can be customized. If you think your campaign will need longer time to observe the effect, then we can expand the time window.